Uh, So this is suppose a brushless DC motor drives. So BLDC, as the name suggests, brushless DC motor drives, permanent magnet brushless DC motor drives, permanent magnet. So three things we will focus here. One is permanent magnet, another is BLDC. Although the motor is AC motor, we need to drive this motor using any DC to AC converter, means like inverter. Still, the name is BLDC. DC comes in its the nomenclature of the BLDC motors, and another the term is permanent magnet. So, the permanent magnet signifies that the rotor of the motor itself is the permanent magnet. So, there is no separate motor. The permanent magnet itself will be a rotor, and the DC in the name of the brushless DC motor drives, we will see there is a term DC. So later we will see in the voltage and current equations of the brushless DC motors, when we go through the mathematical modeling, dynamical mathematical modeling of the brushless DC motor drives, we will find the voltage, current, and phase back EMF equations relations of this motor is similar to that of the DC motors. So its name is DC motor. Now, uh, coming to the electric vehicle systems, in electric vehicles in the propulsion drives, there are several motors that they have been used, like induction motors, permanent magnet synchronous motors, permanent magnet brushless DC motor drives, and several other motors are used, like for e-cycle DC motor is also used. For electric vehicle applications, generally PMSM and PMBLDC motor is preferred these days, as the induction motor is bulky in size, heavy in weight. So to avoid the space in the systems, permanent magnet synchronous motor are preferred. Now, permanent magnet synchronous motor is of two types. One is BLDC motor and another is PMSM. Uh, uh, and that depends on the nature of the stator phase back EMF. See here, means the trapezoidal nature, the top here and the bottom here is EA. So this is the phase back EMF of the motor. So it is trapezoidal in a nature. So it is the brushless DC motor drives, and which will have sinusoidal in nature is the PMSM, permanent magnet synchronous motor drives. Now, coming to the math means this Matlab file, how we can develop the mathematical modeling of the PMBLDCM motor drives. See here, this is a PMBLDCM closed loop systems. This is a PMBLDC closed loop systems. Here we can see we give some reference speeds, and from there we generate some reference currents, and from where we will generate the gate pulse to drive the inverter, and that inverter will be used to drive the brushless DC motor drives. So how to means model means first I am starting that how we will use the equations. Some equations we have here: voltage, current, phase back EMF relations, and here torque. We will have speed, number of poles, power, phase back EMF constants. So many mathematical simplifications are there in the systems we have to deal with. So yes, I will start with how these are the equations of the BLDC motor drives. So this is the dynamic equations of BLDC motor, mathematical representation of any motor. So with this concept, you may be able to model to write the equations in Matlab. I have some relations here: voltage, resistance. Suppose I am considering a phase A. This is three phase motor. So phase A, phase B, phase C. VA, VB, VC are the stator phase back voltages. Sorry, stator phase voltages. RS in all the three equations, in all the three pages, you will see it is the stator resistances. Ia represents the stator phase currents. Stator phase current is given by I for phase A, Ia, for phase B, Ib, and for phase C, it is represented by phase IC. L is the means mutual inductance between all the phases. And sorry, L is the stator inductance per phase, and M is the mutual inductance for all the phases. EA, EB, EC represents the stator phase back EMF of the PMBLDC motor drive systems. Now, some assumptions are made and it has been simplified to the three phase voltage equations. V is equal to IR plus L di by dt plus EA. This is the general voltage and phase back EMF related with the stator phase currents in terms of the resistance and the inductance. So this is nothing but the voltage equations. This is VA, that is the voltage across the phase A, stator phase voltage. This is the RSIA, this is the voltage drop across the resistance, means stator resistance, and the voltage drop across the stator inductance per phase, and this is the phase back EMF EA. Now, how to represent, how to relate, and how to write these mathematical equations in Matlab, we will see here. Further, these are all the phase back EMF equations, EA, EB, EC, and omega R is the mechanical speeds, and Ka, this is actually the K, that is, this is the stator phase back EMF constants, from where we will obtain the equations of the torque in terms of the number of poles and the speed. See, generally we know that the torque, how the torque relation is obtained. So we have the voltage EA, IA, and then number of poles and the means mechanical speeds. P by 2 is the number of pole pairs. Somewhere in equations you can see simply it is small p, and we call it as pole pairs or number of pole pairs. Depends on the representation. Now, actually, before that, some basic concepts of the BLDC motor. See, in BLDC motor or in any motor, we can say here, suppose this is a motor, we have one motor. This is represented as a motor. So, and this north-south pole is the representation of a rotor. This motor has a rotor as a permanent magnet, as a rotor, and that permanent magnet is represented by NS. NS means north pole, south pole. Polarity of the magnets are represented here by north and south. So in case of permanent magnet motors, this is the thing that we should know, that we have some means closed loop, and before that I will explain the difference between the open loop and the closed loop systems. Suppose first I will explain open loop and closed loop. I have two eyes, 6 by 6 eyesight, and any person who don't have any eye, and we are walking on a straight road. The road is of suppose 2 kilometers. Assume the road is of 2 kilometers, and the road is straight. Both the person is walking on a road. The person who has two 6 by 6 eyes, the person who is blind, who don't have the eyesight capability, he is blind. He cannot see anything. If I will walk straight on the road for 2 kilometers, the same person who is blind is also walking on the same road in the same directions. While walking, I will have some distractions. My eyes will give some information to the brain, to the neuro, and accordingly, my brain and my body will act with that information. I can see trees, I can see big, big buildings, I can see the persons crossing me, I can enjoy the nature, weather, everything, whatever I am crossing, whatever crossing me. But the person who is blind, he don't have eye, so he will not be able to grasp those informations. The signals will not be passed to his brain, to the neuro to act accordingly. So what his concentration will completely to start from the source station and to reach the destination stations. He will not have any distractions, he is not getting any feedback signal. I mean to say, the system who is getting any feedback signal is a closed loop system, and the system who is simply getting some input and reaching to the output, from started from the input and reaching to the output, is the open loop system. It is not getting any feedback signals, means from the output side to the input side. So here, suppose this is any system working here. I have given some speed. This is the reference speeds. I am pressing the accelerator, giving some reference speed, the desired speeds, and it is with some signals and with some processing acting on the motor of the electric vehicles. Now, the actual speed of the motor is sensed and given to the reference speeds. Now, there is some, means error amplifier. After error amplifier, what the error amplifier will do, the error amplifier will recognize the system. Suppose my reference speed is 500 rpm, however the motor is running still at 300 rpm, so we need to give some more speeds. Now the error amplifier will get some error in the speeds, and it will amplify those error signals to some equivalent magnitude of the signals. So this is the closed loop systems. So not to achieve this, to achieve the speed of the systems, to achieve the speed of any motor, we have some rotor informations need to be obtained from the rotor, need to be obtained from the motor speed. So how to obtain the speed of the motor depends on the types of the motor. In case of BLDC motors or permanent magnet motors, we cannot obtain directly the speed of the motors. We don't have the information here. We don't have the, suppose this is the motor, we don't have the information to directly obtain the speed of the motor. So at what speed the rotor is rotating of the motor is, means not, means obtained directly. Then how to obtain the speed of the rotor of any motor in case of BLDC or PMSM? Their Hall signals are given. So how the Hall signals can be obtained? This is the Hall signal. This is the means output of the Hall signals. This is C1001110010. This is the means signal output of the Hall sensors. So what is a Hall sensor? A sensor which is made like a disk. You might have seen a disk that we feed in laptop or computer or to see any movie. So this is just like a disk, and on that disk, at the separation of exactly 120-degree electrically apart, three positions are made. So 120 degree if we are separating, then there will be three Hall sensors. So three Hall signals you can see, H1, H2 and H3. Three Hall sensors, three sensors we are using to detect the speed of the rotor, by which we can obtain the speed of the motor. This is the basic concepts that I am giving that can be implemented to any motor. Now that Hall signals will give us, so, and this disk is glued, fixed to the rotor. So the moment when the rotor starts to rotate, the disc will be rotating with along with the rotor, and that disc will give the signals to the hall sensors, and from that hall sensors we can obtain the rotor speed. Now the hall sensors are rotating. See here, I have done it for 120 degree, 60-60 categorization. So from 0 to pi or 2 pi, we are categorizing the sectors into sectors. So suppose 60-60 like that, it has been categorized, it has been divided. So when h1, suppose for this moment h1 is coming, means see here 100 represents h1, H2, H3. So for this section, for sector 1, we can see for these sections, suppose means in between this bold line and the first dotted line, you can see only just I am just suppose I am taking only for first three first three means waveform. So in this zone, in this sector, only h1 is coming, h2 is 0, h3 is 0, means it is 100. Now going to sector second, in sector 2, in between the first dotted line and in between the second dotted line, we can observe h1 is 1, means some signals are coming across hall sensor 1, some signals are coming across hall sensor 2, and there is no signal coming from hall sensor 3. So we are getting in sector 2 as 110. One represents, first one represents hall signal, hall sensor signal 1 is coming, second one is representing signals from hall sensor 2 is coming, and third is 0, means there is no signal coming out from hall sensor 3. So these are all the representations for all the 6 sectors. Now as the motor rotates, there will be some stator phase back emf across all the 3 phases. See here, in case of BLDC motor, the stator phase back EMF is trapezoidal in nature. So this top here I can so see this black, bold black is the representation for the waveform of stator phase back EMFs. It is trapezoidal in nature. So it is flat for 120 degree. See here, this is 60, this is 60. So first two dotted line is 120 electrical degree. So it is flat for 120 electrical degree. And in this zone also, if you see here in bottom line, it is flat for 120 degree. Again, it is flat for. So sometimes it is flat for positive 120 degree, sometimes it is flat for negative 120 degree, and there is transition from plus 120 plus e to minus e. Again it is transiting from minus e to plus e. So when it can be positive or negative depends on the facing of the rotor, whether it is facing the north pole or the south pole. The moment when the rotor is facing, I suppose I am starting with north pole. So for this 120 flat degree, the rotor is facing the north pole, and for this 120 minus, the rotor is facing south pole. What about this region? This is the region during which the rotor is shifting from north pole to the south pole. So this is the effect, it means this is the fringing effect of the magnets. So and so I think this concept is clear that means when either it is facing completely north pole or south pole, then the phase vacuum will be flat. The moment when it is transiting from north pole to the south pole or south pole to the north pole. It is shifting from plus E to minus E. Now, so this is the story behind this. Now see here, this is 100, 110, this is 60, this is 60. So overall it is 120 degree. In case of BLDC motor, the nature of the waveform pattern of stator phase current is quasi-square rectangular, quasi-square waveform. So this is quasi-square representation of the stator phase currents. The moment when stator phase back EMF is plus 120 plus E, stator phase current is also square. And the moment when it is transiting from plus E to minus E, ideally the current should be zero, but immediately the current cannot fall down to zero because of the presence of the inductance in the system. So inductor will take some time to dissipate the stored energy, and again it will take some time to charge the stored energy, sorry, to charge the inductor. So practically this is not possible to make the means this current zero. Now you can means think that why it is required that for the moment when E is plus E, why we want current I, why we want current I to be exactly in aligned with the phase back EMF, because we want the maximum power, we want maximum torque. So E dot I, for the moment when E is available with us, and for the same duration, if we will be able and if we have the capacity to provide the current to the system, then E dot I will be more, means power will be more, and hence torque will be more. And we don't want the current when there is no supply, when there is no stator phase back EMF in the systems. So this is the story behind the Hall sensor input signals. And from here we will see how we obtain the theta. And once we have, what is theta? Theta is nothing but the when the rotor is rotating, suppose we have rotor rotating, so this is, and it is rotating with some angle, so this is represents the angular orientation of the rotor of permanent magnet brushless DC motor drive. So theta is the angle with which the rotor is rotating. Once we have theta, then we can obtain a speed with the relations by either by differentiation, or if we want theta to speed, or speed to theta, from speed to theta. Somewhere we will see that from actually one, we initially we have to take theta from means we will get theta, then from theta we will get some speeds, and from speed in some control systems like dq, means when we will uh, play in two phase systems, dq plane or alpha beta, there in designing the control systems we need the information of the theta. So again from a speed we need theta. So in that case what we will do, either we can use differential d by dt or integral 1 by s to obtain theta or omega. So this is sometimes d by dt or sometimes integral, like that we can obtain theta. Now we will see how to so this is the representation of the BLDC motor drives, and this is one voltage source converter. We have some input side DC, and this voltage source converter is type of converter. We call it as a means voltage source inverter or voltage source converter. This is a inverter which will convert the DC signal into the AC signals, and that AC signals will be used to drive the BLDC motor drives, and there will be some load connected to the BLDC motor drives. Now, coming how to write the mathematical equations in Matlab, that I want to show you. I think I will run this system. Suppose, sorry. Systems. So, I think both copy is visible, PDF and Matlab. Anyone can respond, please.
Yes, sir. Both are visible.
So I am starting with equation 3 first. See, let us take phase A for the illustration purpose. So there is VA is equal to IR plus LDI by dt plus EA. We have here from phase voltage we are getting VA, VB, VC. Suppose this is for phase A, top one is for phase A, middle one is for phase B, and then there is phase C. So we have VA here. We are getting, I will explain how I am getting it. Means this one. So here I am getting VA. Now VA minus EA will be RSIA plus LDI by dt. So BA minus EA. How I am getting EA? I am getting EA from the speed omega r and with some stator phase back EMF constants Ka theta. So for now, just assume that from somewhere I am getting EA. So this is EABC. From somewhere I am getting EABC. So I have here VA and at this DMUX I have some signals EABC. So from here VA minus EA. So till this part I am done. VA minus E. Now, what we will have? We will have Rs Ia plus L di by dt. So, this will have some, if you take Ia separate from RSIA and LDI by dt, we will have some transfer functions there. So now we will write some transfer functions here for RS and L. And C, for all the phases RS and L, I have taken LA is equal to LB is equal to LC is equal to L, and the starter resistance is same for all the three phases. So we will have some, means you may be knowing that we can how to take this, simplify these equations. So this will give some current equations. So from there we will have, this is how in the transfer functions we can write L and R. Okay. Now, so from there VA minus EA upon some transfer functions I is equal to IA. So there I am getting here IA, from here I am getting IB, and from here I am getting IC. So we will have from here VABBC and EBEC, we are getting IA, IB, IC. So this is the starter phase currents of the BLDC motors. Now, see here, I am doing some product. There in Matlab, we have some symbol of summation, some means and for products. Now, what I am doing here, we have I here. This is IA. IA into multiplying by something and getting something. So what I am doing here, we have some Ka, Kb, Kc value. So K into I, Ka into Ia plus IB into KB plus IC into KC. So now this is KAI, this is KBIB, this is KCIC, and adding all these three terms. So this will be, here we will have KAI plus KBIB plus KCIC into P by 2. See here, KI plus KBIB plus KCIC into P by 2 is giving electromagnetic torque of the motor. So here I am getting TE. So this is now, here we have TE. Now this was the electrical dynamics. Coming to the mechanical dynamics, we have here electromagnetic torque, we will have some load torque. So actually I have not written somewhere these equations, somewhere I should have. So I would have written it somewhere. This much equations leave the last term. We are familiar with this type of equations, mechanical dynamics of motor. TE minus TL, we can see TE minus TL is equal to B omega plus J d omega by dt. That is the means mechanical dynamics of any motor. So coming to now MATLAB, we have here T, this is load torque. So then plus symbol minus symbol. So this will be TE minus TL. Should I write these equations? Matlab is visible.
Yes, sir.
So you can see here, is, this equation is now visible. T minus TL is equal to J d omega by dt plus B omega. So here actually uh, J is the means rotor inertia and B is the viscous damping, and J is responsible for converting the torque to the acceleration. So from J converts the torque to the acceleration, and 1 by S, you can see here 1 by S integrates the acceleration to the speed. You can see here 1 by S integrates the acceleration to the speed. So now P by 2, after this I am getting T, the TE minus TL. So 1 by J is equal to TE minus TL minus B omega. So after integration, we are getting here omega. You can see here. This is omega. This point is omega. This is omega. This point is omega. So this is overall the mechanical dynamics of the motor. Te minus TL minus B omega is equal to 1 by J into d omega by dt 1 by S. And now this is the, at this point we are getting mechanical speed of the motor. So with this mechanical speed of the motor, there we have some relations. So electrical speed is equal to means mechanical speed at p by 2. This is from these relations we are getting the electrical speed of the motors. Now from here we are getting the omega e, that is the electrical speed of the motor, and so this is omega here, and integrating this 1 by S is giving us theta. So see here, this is theta, this is theta, this is omega. So after once we have omega, we are integrating to get theta. So this is sensor based signal, means signal based systems, sensor signal based systems. We are using here Hall sensor signals. Now so this was how to means write the equations, any mathematical equations, how to model, we call it as modeling of any mathematical equations, dynamic equations. Now see, once we have theta, once we have theta, then from theta we can obtain ea, eb, ec. So we have some constants ka, kb, kc. So from theta, how to obtain the equations, how to obtain the radians and this EBEC, that I will explain. See here, EA. So we were multiplying the rotor mechanical speed with some phase-back EMF constants to get EA, EB, EC. And I will also explain why I am using cos and sine. This is favor to some compensation angles. Now giving some reference speeds and generating the current reference. From there, using the hysteresis controller to generate the gate pulse, and that gate pulse is given to the inverter, three phase VSI, and that VSI used to drive the BLDC motor drive. So we have run this system. This is three phase back EMF. We can see this is trapezoidal in nature. Here, you can see here. This is trapezoidal in nature. Now IAIB this is quasi-square waveform. See here, this was the point where we were expected to achieve the zero currents. So I tried to means design the control algorithm in which still it is not exactly zero, but with some fluctuations across the zero axis, I am getting the zero currents for the moment where the stator phase back EMF is zero. So this is for phase A system. Uh, this was phase voltage top, and this was stator phase back EMF for phase A, and this was stator phase currents for phase A. This is for theta and motor speeds. Now, see, in this system, I am using Hall sensor signals. So in Hall sensor signals, if I explained you that for any systems I am using some disk. Over the disk I am fixing three sensors exactly 120-degree electrically apart. Exactly 120-degree electrically apart. So means being an electrical or mechanical engineer, we can think and assume that if we insert any disk or suppose any sensor or any things, then it will occupy some additional space. Some mechanical space will be required in that system. So it will increase the volume of the system. Some additional space, mounting space will be required for fixing, for gluing, for installing, for mounting the Hall sensors in the systems. Again, so this was one of the disadvantage using the any sensors. Now, the another disadvantage that we can accumulate is there may be the risk that either of the signals, in this case we are using three Hall sensors, all are 120 electrical degrees apart in 360 degrees. If we are aligning at 120 electrical degree, then we will need three hall sensors. So suppose means there may be the risk, there may be the chance that either of the hall sensors may get damaged. Then the signals through which we were decoding the speed can be means wrong can give wrong information. We may not get exact information from the hall sensor signals. This was the systems that I explained. We were getting some signals from the BLD. This was the encoder. Here we were getting HA, HB, SC that we were decoding to get the either if some systems can get reference, so it means feedback speed or directly reference speeds can be obtained from there. This was the hysteresis control that we have discussed already. This is the inverter. So the one risk was damaging of the hall sensors. One disadvantage was extra spacing. So to purchase this disk hall sensors, we will have to invest some amount money. So it is also costly. This was the third disadvantage. Another disadvantage is that while aligning exactly at 120-degree, there may be the chance that some with some angle there may be some deviations while mounting, while spacing, while fixing these all these three hall sensors. So it cannot be, it may there may be the chance that exactly at 120 electrical degree we cannot fix all those all sensors. So still there will be some deviation. There are multiple disadvantages using the hall sensor signal. So to avoid those systems, we are avoiding to overcome these limitations. We are switching to the sensorless systems in which we will not use the hall sensors or any optical encoders. We will not use any encoders to obtain the angular orientation of the rotor and hence to obtain the means rotor speed of the motor. In case of BLDC motor, in case of permanent magnet synchronous motors, what we can do, we can go for sensorless operations. That means, as the name suggests, sensorless operation means the system which will have no sensors to obtain the angle orientation of the rotor or to obtain the information of the motor speed is the sensorless scheme. So before going to the sensorless scheme, I will also explain another type of means this is also the control of the BLDC motor drives. So one was using the hysteresis current controller. This is using the means synthesis method in which instead of using the means three phase signals A, B, C, we can use only two phase, either in DQ or alpha beta plane. And this will means the main objective is means behind this DQ or alpha beta plane is that you can study somewhere what is DQ and alpha beta, stationary and rotating reference frame it is. So actually in layman language I can say that this is the way with which designing of any controller is easy. It is in DC, so we can design any controller in the easy way. Now let me explain with this diagram. Let me explain. So this was the same results that means we have seen. More results I will show. So means another module of my work was to make the controller design easier. And here we can see that at means in any sector from left to right, you can see in any sectors only two phases are conducting. Suppose I am explaining sector 1 from bold to the first dotted line. Here we can see IA is there, IB is there, forget about whether it is positive or negative, but IC is 0 here. So only two phases are conducting at a particular time. If we see in sector 2, first dot line, in between first dot line and in between the second dot line, we can see here that IA is there, IB is 0 and IC is negative. So plus IA, 0 minus IC. So in this sector also only IA and IC are conducting. So in any sector we will see at a particular time in a particular instant during some interval only two phases are conducting. Now coming to the petal wave structure, the method that we will discuss now is referred as petal wave. See, this looks like a flower that resembles like petal in structure. So we call it as petal wave structure. Means here, see, what I have done here is I have used simple straight line equation y2 minus y1 upon y minus y1 x2 minus x1 x minus x1 with the simple equations. This is a straight line equation, right? Visible?
Yes, sir.
See here, from here, from the straight line equations, for any sector I am considering, this is for sector 1, suppose it is increasing or decreasing like that, y is equal to mx plus c. And from the relations of y2 minus y1 and x2, y2 minus y1 by y minus y1, x2 minus x1 by x minus x1. So for each sector, I have calculated EA, EB, EC, IA, IB, IC. Simple equations, slope equations for each IA, IB, IC for all the 6 sectors. I have considered to each 6 sectors. Sector 1, sector 2, sector 3, sector 4, sector 5, sector 6. And from there, after obtaining all the 6 sectors values, we got some E alpha, E beta, I alpha, I beta for all the 6 sectors. Here interval S1, S2, S3, S4, S5, S6 are all the 6 sectors. So from 0 to pi at 60-degree time interval. So E alpha, E beta, I alpha, I beta has been obtained using the relations. First I have obtained EA, EB, EC, and from the means 2 axis reference frame, means any X alpha and X beta can be transformed from X, XB, XC like that, using this matrix equations, parts transformation. And there, from that E alpha, E beta, I have done here in this tabular form. And now I will explain how to develop the modeling of this equation for the BLDC motor drives. Now coming to this part. So this is We call this method as petal wave current injections method. See here, this looks like petal wave structure. So whatever the means theoretical assumptions were there has been proved in Matlab using that mathematical dynamics equations, and also we will see the improvements in the results, reduction in the torque ripple contents and improvement in the motor parameters. Now how it has been done? It's coming. No, this was not the file. From petal. So we have seen, we obtained theta. So that theta was in degree, and we need the theta in radian. So this is the way method to means change the theta from degree to radian. So what we will do, we will multiply some k value. This is compensation actually here. Radian to degree I will change later. I was explaining here why I have used theta, sine also, cos also, and what is the significance of using a tan 2. So actually, wherever the theta comes into picture, we want to check the quadrant. So these values, sine and cos, in modeling, these values are used to determine the correct quadrant of the angles. So whether it is positive or negative, but we want to use the correct quadrant of the systems. And a tan 2, here a tan to consider both signs of the cos and the sine components. And output range wherever we require the radian to theta, then there we will multiply some with some k constants. That means 180 by pi, and it will give degree to radians in radians. So already I have explained that means we will have 6 sectors, and in that 6 sectors, what we will do, we will model, we will see the mathematical modeling of I alpha, I beta, E alpha, E beta. Suppose here, this is for sector 1. I am considering first, this is, you can see here, the caption for all the sub blocks are represented: sector 1, 2, sector 3, sector 4, sector 5, and sector 6. We will see 1, 2 sectors now. From somewhere I was getting mu. Mu was nothing, but it was a common term in all the equations, whatever the equations I was obtaining. So in all, somewhere I have written some equations, I think. Let it be. Let me go through my original documents. Event that I'm one, two, two is here, four is here, six is here. Actually, I think I missed to put it here. No problem, I have in PPT. Okay, let me explain. Actually, mu was a constant in all the equations of the sectors. It was a common term that I was obtaining. So I replaced those systems, those variables with a common term here, mu. In these derivations, we can see. Suppose this was obtained for sector 5 and sector 6. Sector 6 is completely visible. It was from 3 pi by 2 to 11 pi by 6. Let me explain at least once. One for sector 6, from 3 pi by 2 to 11 pi by 6. This was sector 6. Here we see EA is equal to plus, EA is equal to minus E, EB is equal to some with E values, and EC is equal to plus E. I will explain for one sector for my satisfaction. It will be better view. 1, 2, 3, 4, 5, 6. Coming to this here. Suppose this is if sector 6, then somewhere this, suppose this is some phase vacuum. So here it is minus E, here it is plus E, and it is transiting from some values from this axis minus E to plus E, and it will have some x axis, some y axis, some x-axis, some y-axis. So here it is minus E, here it is plus E, and on the bottom side, suppose it is means 9 pi by 6 to 11 pi by 6. So we will take one reference values to obtain those means equations. So it can be plotted like this. It can be means derived like this. Will have some means pi by 6 regions, 9 pi by 2, 11 pi by 2, or 6, whatever it was, and it was transiting from some values plus e2 minus value. So using those equations, y2 minus y1 is equal to x2 minus x1, by sorry, y2 minus y1 by y minus y1, x2 minus x1, x minus x1. From that relations we can obtain these values for all the 6 sectors, and some terms were common in all the sectors, so we have replaced it by mu. Likewise, it has been obtained for all the 6 sectors that was means presented in that table, in this table. Somewhere I might have written the values of the mu. Let it be, it is not required now. So now see, for all the 6 sectors, E alpha, E beta, I alpha, I beta is obtained. And coming to the Matlab, suppose I am coming to this sector 1, and PPT also I have written somewhere, at least for one sector. Mu was coming, mu was nothing, some with some constants I have written mu because it was common to all the terms, so I have taken some mu. Mu was here, see, we can see here, it was means 2 by pi into theta is giving mu. So from mu into 2 is 2 mu. We will have here, see here, 2 mu. At the bottom we can see here it is 2 mu by 3 mu square plus 1. So from here it is mu square into multiplying with some gain 3. So this will be 3 mu square and plus 1. So this is 3 mu square plus 1. This is 2 mu. 2 mu, then we will take a product block. We can select from the library. This is the library browser. You can directly search from the search button, or we can, here we can write product. You can search. This triangular shape is again. We can also double click in this window, and we will be able to just write, and the library will give that block. See here, this is a product block. We can drag it, we can add to the systems. If you will double click over it, we can increase the number of ports. Whatever the ports we want, we can increase here. We can also simply write here, and we can get. This was go to and go from. I will also show somewhere. Go from will come somewhere. So this was 3 mu square plus 1 into 2 mu divided by 3 mu square plus 1. See here, into I will come. I will explain that one. So this was I alpha for sector 1. Now coming to the I beta for sector 1. It is 1 by 3 mu square plus 1 into I. This is I reference. This is mu getting from the previous one here. So now we have to model for the beta part. Minus 2 by root 3, 1 by 3 mu square plus 1. See here, till this point, we were getting 3 mu square plus 1. So if we will do 1 by 3 mu square plus 1, till this point, this output was giving 3 mu square plus 1. So we are taking 3 mu square plus 1. Now 1 upon 3 mu square plus 1. One upon 3 mu square plus 1. This part is completed into minus 2 by root 3. So this is again value minus 2 by root 3. Here we will write what we want. So in Matlab we will write square root 3 like this, minus 2 by square root 3. So this part, numerator part is completed into I. Now we have to multiply with I for I beta sector 1. So we have here I is multiplied in alpha also, alpha component also, I is multiplied in beta component also. So what we will do, we will take a product, and there we will go to multiply this with I in both the systems. So here we achieved I alpha and I beta. So this is the way to write the mathematical equations in the MATLAB, how to model any systems. Here we were getting IAIB, mu I reference. We can see in the same way for sector 2. This is for sector 2. Sector 2 derivation was 1 plus 3 mu. upon 9 mu square minus 12 mu plus 7. So 1 plus 3 mu in numerator part. Denominator part is 9 mu square minus 12 mu plus 7. Mu was coming here. From here mu was coming. So 1 plus, first what we will do, what we need, we actually need, we want in numerator part 1 plus 3 mu. So we have a mu. If we will multiply by 3 in mu, this is a gain. In search you can simply write gain. You will get here like this gain value. Whatever you want to write here, write whatever you want. So we want 3 mu. So what we did, we multiplied mu by 3. So we obtained 3 mu. And then in numerator part, we want 1 plus 3 mu. So what we will do, we will 1 we will take, and we will take a sum block. We will add 1 plus 3 mu. So numerator part is completed. Now what we want, now what is remaining, denominator part is remaining, and then we have to divide 1 plus 3 mu by this denominator part. Denominator part is 9 mu square minus 12 mu plus 7. So we will take some mu square. We already have mu. Now we have to just make it a square. So we are making it a square. This is mu square. What is our requirement? 9. First requirement is 9 mu square. We have now mu square. We will multiply it by 9. So this part is completed. Our task 9 mu square. What is our next task? To obtain minus 12 mu. This is already mu. From here we can multiply it by 12, or we can multiply by minus 12 and we can simply add here. So I am multiplying it by 12. So this part is 9 mu square, this part is 12 mu, and what else is required remaining? Plus 7. Simply taking some constant block with 7. So this block output will give us 9 mu square minus 12 mu plus 7. So this was for denominator part, this portion was for numerator part. Now numerator upon denominator, what we will do, we will multiply by I reference, will give some I alpha, and this was all the above portion, this portion was for I alpha. Now coming to I beta, this is for equalizing this screen. So now coming to I beta, I beta, what we have, mu minus 1 is our target for numerator. We have here mu, we have mu. So mu multiplying it with 1 is mu, subtracting by 1. So this one is numerator part. Here we got mu minus 1. See here, mu minus 1 is completed. Now our denominator is 9 mu square minus 12 mu plus 7. That is similar to the denominator of alpha component. So here it was 9 mu square minus 12 mu plus 7. Simply we are connecting it here. So numerator by denominator, multiplying with some constants. With what constant? 3 root 3. This must be 3 root 3. See here, 3 root 3. We will give some values. We will multiply with I. It will give some I beta value. So this was for sector 2. So similarly, for all the sectors, this data web structure has been modeled, and it was the means theoretical assumptions, and means Matlab modulation was this. Matlab modeling was this system, and then here we have seen already this was means stator phase voltage, stator phase back EMF, stator phase currents. This was the motor speed and the theta in radians and in degree. So this is the petal wave structure of the stator phase currents. Here we can see the implementation of the stator means petal wave structure in injecting these petal wave stator phase currents to the systems, and this is the behavior of the systems, how the torque and the speed of the motor is varying. If you want, I can explain. This was the mathematical modeling of any systems in Matlab, and this was all the experimental setups. You want, I can go in detail, but if it is useful to you, experimentally it was also obtained the petal wave structure. In some paper I have shown it. See here, this is my paper. Experimentally also I have obtained this petal wave structure for all the 6 sectors. So this was the experimental setup. You want anything to know, I can explain. You want, you want to, you want me to continue, or it is enough, whatever. I'm waiting for response. Whether should I continue or should I stop at this time? Or if you have any questions, want to know anything, we can discuss. Okay, means let me give some. Please give me some more time. Screen visible now.
Yes, sir.
Actually, the topic, whatever the topic I have given, was incomplete. No, here what we have seen, that we are just giving some AC signals to the means to motor, and that motor is used in electric vehicles. Suppose in case if we have number of sources, we want to integrate our system with different number of, with different types of energy sources, power sources, or we have means varieties of loads at a singular time, at a means single time. At the same time, if we want to integrate to run our systems from different types of sources, it may be the electrical supply in our lab, in our residential units, in our grid, in our society, in our colony, or we can use some PV sources, we can use some battery energy storage system, we can use some wind energy, we can use supercapacitors as a source of energy. So that can be possible using some. Let us take example of any electric vehicles. In electric vehicles, if we ride in a car, there is a AC motor. It may be induction motor, it may be PMSM, it may be BLDC motors. Please listen carefully the story. So if we ride in an electric vehicles, in any car, in any e-rickshaw, any e-bus, whatever it is, in any vehicles, there is AC motor. So to feed the power to drive that motor, we need some DC to AC converter because the motor is AC motor. So we have to give AC nature of voltage and currents to drive that motor. AC signal is required. At the same time, there is battery in the electric vehicles. So battery is DC in nature. To drive that, to store the energy in the battery or to take the power source from the battery, we should have some DC-DC converter there. So for AC motor, we need DC to AC converter, that is inverter. For battery, we need DC-DC converter, buck boost. For different applications, sometimes we need AC to DC converter. So in a single electric vehicle, in a single car, see, for different types of applications, we need to dedicate different number of converters in a single car. Suppose if we talk about any smart building, we have a smart building SVAC system, that we call it a heating ventilation AC system. In SVAC systems, we have we need AC in our room, in our lab, and sometimes some zones are there where cold water is required, chilled water is required. During winter we need blowing, means hot air in lab, water needs to be heated. So in any smart building system, in any SBSC systems, we have some chiller plant that will cool the water, that will give some steam to make the water hot. We will have some radiator, the fans that will blow the cold air or the hot air. We will have some water pumps required, means in the HVAC systems. For the AC system also water is required. So different number of equipments are there in a building. In any mall also you can see these things. So for every equipments, for chiller plant to make it cold, there is a big motor. For that, different one big converter is dedicated converter is required, because it is a motor, compressor is a motor. So there will be DC to AC converter. For water pump, there is a motor, separate converter is required. For radiator fan, there is separate motor. Somewhere it is battery, different dedicated converter. So in a single system, some AC DC converter, some DC AC converter, some DC DC converter, so rectifier, inverter, buck converter, boost converter, lots of converter is required in a single system, either in electric vehicle, in a smart building, or in any SBC systems. So many systems to replace those different converters. Inverter is a type of converter which will convert DC signal into AC signal. Rectifier is a type of converter which will convert DC into AC, AC into rectifier, AC to DC. Sorry. So see here, AC to DC is rectification, DC to AC inversion. So rectifier and then inverter. So to replace those different number of dedicated converters, we can design one multi-port power converter, which in which a single power converter is capable to supply to where we can give multiple number of, means energy to be integrated. Suppose this is a multi-port power converter. Here, see here. Suppose this is AC terminal of any motor. So this converter is giving supply to the AC motor, but At the same time, we have different DC here, DC1, DC2. This DC1 can be a battery, this DC2 can be a battery, or any PV or any EV charging stations. So in a single converter, we can integrate this AC, maybe grid, maybe motor, like that. So in a single converter, we can integrate different number of sources. This DC1, DC2 is source, PV, battery, like that, and number of AC sources can. This is for illustration purposes. And this simple converter, multi-port power converter configuration here, sometimes it acts as a buck boost converter, sometimes it acts as a full bridge converter. So in each leg, what we are doing here is we are using some boost inductor. That boost inverter is capable to perform the buck boost operations with the help of each leg of this converter. Different number of configurations can be obtained from this type of systems. So this was different type of means multi-port power conversion systems. This is non-isolated because there is no transformer in these systems. You can see there is a transformer in between these two stages of the converter. In this system, see, electric vehicle is used for EV charging station, grid is there, PV panel is there, battery energy storage system is there. So in a single system, with the with the help of the single power converter, we can integrate it to electric vehicle, battery, PV, grid. So like this is another configurations of the multi-port power converter, where we can have PV, EV battery, grid, or any motor. Like, and this is the controlling methods of this type of systems. This is the applications where multi-port power converter can be used in electric vehicles, in smart agricultural farming systems. See here, for means irrigations. These are for irrigations, for harvesting, for cutting, for digging the soil. In defense sectors, in planes, this is wind power plant. This is also farming tools. So number of applications are there for these types of systems. Okay, thanks from my side, and I am done with this number of slides. If you have question, you can ask, or